Hello class, in the last time we are talking about the performance of cellular downlink. In this class we will continue the discussion. Okay, so in the last class we have computed the mean of the interference condition on the location of the serving base station, and it was given as 2 pi lambda pt divided by minus alpha plus 2 into r to power minus alpha plus 2 with the limits from r0 to infinity. Now this final answer will depend on the value of alpha. Let's take the first case where alpha is greater than 2. In that case, minus alpha plus 2 is negative. So I can change r to power minus alpha plus 2 as 1 upon r to power alpha minus 2. Now alpha minus 2 is positive. So the r will remain in the denominator with some positive exponent. If we put the limits infinity and r0 into this, we will see infinity limit will become 0 and the r0 limit will give some value. So the final answer would be 2 pi lambda pt divided by alpha minus 2 into r0 to power alpha minus 2. Now this one is a finite, interference finite here, which is different in the magnet case, and the reason being because the lower limit of the interferer location is cannot be very close to the user. There is some exclusion ball r0 and the interferer only start after that ball. Let us take the case when alpha is less than 2. In that case you will see alpha minus 2 is actually negative, so it will come in the numerator with some coefficient. When you put infinity limit, the whole terms become infinite. Same case would be with the case when alpha is equal to 2. You will see some log terms and the overall interference will become infinite. Now after the mean, we will move back to the Laplace transform of interference, which will actually characterize the interference. So again we will condition on the distance of the serving base station from the user, which is x0 equal to r, norm of x0 equal to r. Condition on that we will compute the Laplace transform. Again, using slave-rank theorem, we earlier said that distribution of I and distribution of I2, which is from an independent PVP, is the same. So the Laplace will also be same. So to calculate the Laplace of the interference I, we will calculate the Laplace of interference I2. Now this we just say the same thing, and again I2 is not is from phi, which is not conditional on x0, but I2 is a function of x0 because the interference in we have a indicator term that norm of yi is more than norm of x0, which just means that we are only taking those base station from phi 2 which are outside the ball of x0, and this indicator is because of the association law. So the expectation of e to power minus si2, we just replace the value of i2 as summation of hipt yi minus alpha multiplied by the indicator term yi greater than s0. And this expectation with respect to phi and hi. So this is a mark point process, so you have to compute the expectation with respect to hi and phi both. Now because exponential of some summation can be written as the product of the exponential, same thing you can write as multiplication over all yi of exponential minus shi pt yi norm minus alpha multiplied by the indicator that norm yi is more than norm of x0. Now we can directly apply the mark point Poisson point process PGFL, or we can do by fundamental steps also. So what I do is condition on yi, I'll take hi's are independent, so I take the expectation with respect to h inside of the product term. Now the inside term will have expectation with respect to h, so the whole term will be some function of y. Okay, so this can be we can apply the PGFL because it is expectation with respect to phi of product terms of Fy, where Fy is in this particular format. So we can apply the PGFL and then we can say that this is equal to exponential minus lambda integration of 1 minus Fy, and Fy is this particular function. Now we can again convert to the polar coordinates, and then y become y dy, there will be 2 pi terms because of the angle, and then the inside will be 1 minus expectation of h of exponential minus sh pt y minus alpha. Now, but one thing to notice that the integration range is from not from the 0, it's actually from r0 to infinity, and that is because the interference, when you're summing it, it's only coming from the interference which are outside the ball of r0. So now we can notice that fading is an exponential random variable, so the expectation of h term you can solve using the moment generating function of exponential random variable, which is 1 upon 1 plus s. So using that we can further solve the interference, and then the Laplace of the trans finally you get as exponential to power minus 2 pi lambda integration from r0 to infinity 1 minus 1 upon 1 plus s pt y minus alpha integration with respect to y dy. So after characterizing the interference, let's come back to the original matter we are talking about, the coverage probability. So recall the coverage probability is nothing but probability that SINR is more than threshold. Now there are multiple random variables in this probability. One is the interference, one is the serving base station distance, and the fading caused by phased at the serving base station. So we will decondition one by one. So first we will condition on R0 and write probability that SNR is more than threshold condition on R0, and this will be we will decondition with respect to the R0. So there is expectation with respect to R0 outside. Now expectation with respect to any random variable is just integration with respect to a distribution of that random variable. So this will be equal to integration of the term probability that SINR is more than tau condition on R0 into distribution of R0, which is FR0 R dr. This distribution we have already computed, so we'll just put back the value here. This will be integration of the conditional probability that SNR is more than threshold e to power minus pi lambda r square into 2 pi lambda r dr. Now if you look the inside term, SNR is more than threshold condition on the value of R0. Just put back the value of SNR, which is H0 into transmit power PT into R0 to power minus alpha, which is actually equal to R to power minus alpha here because of the conditioning, divided by noise plus interference. So here the random variables left are I and H0. That is the probability term. So what I do is I just leave the H0 term this side and move all other terms to the right hand side of the greater than sign. So this term will become probability that H0 is more than tau sigma n square plus that I plus that will come in the front top, and then PT will be 1 upon PT and R0 minus alpha will be R0 plus alpha or R to power alpha because of condition, and the whole term is condition on R0's value. Now again remember this term basically has two random variables left, H0 and I. So we will again decondition those one by one. Inside I'll condition on I, and condition with respect to R0 is already there, and then this value I'll decondition with respect to I outside. So it will be E2 expectation with respect to I, and then probability that H0 is more than tau pt minus 1 R0 to power alpha sigma n square plus R. Okay. So now this probability that h is greater than something, h is an exponential random variable, so probability that h is greater than a is equal to e to power minus a. So because of that reason, probability that h is greater than this term is equal to exponential minus that term, which is tau pt minus 1 r to power alpha noise plus interference. Now we have to compute this, decondition this respect to I. So it is e to power minus, I'll first break this sum into noise and interference separately. So one would be e to power minus tau pt minus 1 r alpha into noise sigma n square, and that does not depend on I, so we can take it outside the expectation with respect to I. So this will just become e to power minus tau pt minus 1 r to power alpha into noise, and the rest term is exponential minus tau pt minus 1 r alpha into I. That is, if you look at that term, it is e to power minus I into something, and when you compute the expectation with respect to I, this is nothing but the Laplace transform of I computed at that particular multiplicated term. So this term will become just the Laplace of I evaluated at tau pt minus 1 r alpha, and this is again condition with respect to r naught. Okay, and recall Laplace of I we have already computed, which is equal to Laplace of I2. So we will just put back the Laplace value here evaluated at this particular term, and that is how we are going to proceed. Okay, so now we put back the Laplace transform in the probability coverage expression, which was 2 pi lambda into e to power minus lambda pi r square, probability that SNR is more than threshold, condition on R naught, RDR. And that was equal to Laplace transform, so we'll just put the value back, which is e to power minus tau pt to power minus 1 r alpha sigma n square into Laplace with respect to I2 evaluated at tau pt minus 1 r alpha. And if you put this value in place of s in the Laplace function, you will get exponential minus 2 pi lambda integration from r to infinity tau upon tau plus x by r to power alpha x dx. Now we can do some manipulation. We can put a new variable u equal to x by r square tau minus 2 alpha, and the integration will be converted to exponential minus pi r square lambda rho tau by alpha. Now this rho tau by alpha is a new function which is equal to tau 2 by alpha integration from tau minus 2 by alpha to infinity 1 upon 1 plus u alpha by 2 d. This can be very easily found just by, if you do the substitution, you will see that this term will come naturally. Come to the final solution of probability of coverage, which is equal to 2 pi lambda into e to power minus pi lambda r square e to power tau pt minus 1 r alpha sigma n square and exponential minus pi r square lambda p tau by alpha r dr. Now this is the final result, and sometimes people just substitute v equal to r square also, and that will further simplify. It will make r square to v and remove r dr term to dv to give you almost similar form. So now to notice in this is this exponential minus tau pt minus 1 r alpha sigma n square term is because of the noise. This e to power minus pi lambda r square r dr term, that is because of the distribution of the solving distance, and exponential minus pi r square lambda rho tau comma alpha, that is term because of the interference. The expression of the probability coverage we got is a very simple one, and we can numerically solve it, and the only question is to calculate rho tau comma alpha function. But we will also present some special cases which will make the analysis much more simpler. So first we'll think is the interference limited case. So in normal practical scenarios of modern wireless, noise is not an issue. The transmit power is enough so that the noise become negligible in test scenarios. And actually main problem is the interference, which limits the assigner and hence the performance. Such systems are known as no noise or the interference limited case. We'll also keep alpha equal to 4. That will make analysis little bit easier. And this is a fairly typical value for the terrestrial propagation at moderate to large distance. Now we will take the first case, interference limited, any path loss exponent case. Okay, so this is just mean the noise is 0. So you put back the sigma n square equal to 0 in the probability coverage expression. And then once you put that, you will only have terms e to power minus lambda pi r square multiplied by e to power minus some r square term into some multiplication dr, rdr. So this can be very fairly computed because of the exponential terms. So once you put v equal to r square, this integration will be written as pi lambda integration from 0 to infinity exponential minus pi lambda v, and then one term 1, and the rho tau comma alpha comes from the interference. They can be written as 1 plus rho tau comma alpha dv. Okay, this is just exponential to power minus ax dx term, which will be equal to 1 upon a. So this will be written as pi lambda divided by 1 upon pi lambda 1 plus rho tau alpha. Pi lambda cancels out, and you only get 1 upon rho tau comma alpha. So this is a very simple expression. There is no integration here. Just you need to know the value of rho tau alpha, which is a simple function of tau and alpha. And then this is the answer you get. Now just for a specific case, we put alpha equal to 4. In that case, rho tau comma alpha can be computed as from the definition of rho, tau 2 by alpha, which is 2 by 4, integration from tau minus 2 by alpha, which is tau minus 1 by 2 to infinity, 1 upon 1 plus u alpha by 2 will become 2 du. Now 1 upon 1 plus u square du is a very standard form and can be computed by substitution of tan theta. So you will get final answer as tau square root of tau into tan inverse of square root of tau. Okay, so if you put back this expression, the probability coverage will become 1 upon 1 plus square root of tau into tan inverse of square root of tau. Now there is no integration in this term, and we can very easily compute this for any value of threshold, because tan inverse is a well-known function. Okay, this is a very simple expression. You can very easily see that if you put tau equal to 0, this will be equal to 1. If you put tau equal to infinity, this will be 0. You can even plot this at tau equal to 1. You can also compute it should be equal to tan inverse 1. That can be very fairly computed. Okay, so for just for the numerical value, if you put tau equal to 1 here, which is 0 dB, which means the rate is will be maximum 1 bits per second, the probability of coverage will come out to be 0.56. Now you can see this is very low case because 56% of the coverage is very small. Okay, and even when the rate threshold is so low. The reason is because this is a pure very simple case, and normally we will also use sectoring, which can reduce the interference, because you are only focusing all the power in one case. We apply other antenna gains also, and not all the base stations are transmitting all the time, so that will further reduce the interference, which can improve the coverage performance little bit. A very simple insight which we can derive from this result is, you can see in the interference limited case, or you can say the SIR coverage probability does not depend on lambda. So it means whether we put 1 base station or 100 base station, the SIR coverage will be same. So this result was known earlier also, but technically we can prove it. We can show the result using stochastic geometry, that the coverage probability, SI coverage probability, does not depend on lambda. And that property is actually known as SIR invariance property. For alpha equal to 1, we can also compute the probability of coverage in presence of noise also. In equation 23, you will notice that there is an additional term tau pt minus 1 sigma square v square when there is noise. So the whole form you can notice is e to power minus v into something minus v square into something dv. So this can be uh, very much solved by using the form equation 25, which shows that if you have to integrate e to power minus ax into e to power minus bx square dx, you can use this form. So using this, we get the following expression 26, which requires the evaluation of this Q function, but that is fairly easy to compute. We have seen that analysis can actually help us to understand or derive some insights of the system, which simulation cannot. But a natural question to ask here would be, yes, we are able to derive some results, but are those results accurate? Do those results actually describe the real world cellular networks, which do not have Poisson distribution? And if you talk about this real cellular networks, they are deployed in more strategic manner than just the random deployment. While the Poisson base station distribution, if you see, some of the base station can be very close, some of them can be very far away, because the points are all independent, they can be anywhere. And for this region, the real cell networks are more close to something like a regular grid, like they can be put in a grid of squares of or the hexagonal grids which you have seen earlier. But basically, this is also not true completely, because yes, you want to put a strategic deployment, but there are two things. One is you cannot put base station anywhere. There may be a river there or some other geographical constraint would be there. And also, sometime depending on which area have more users, it can have more base stations there. So it's also not very much equal to a square or hexagonal grid, and it's also not very close to the PPP deployment. A real scenario is generally in between. So even if you look at the conventional, when we do simulation, we generate a grid-based base station, but then we perturb these location of this base station by some Gaussian amount, such just to model that randomness of the base stations. We can see an example of a PPP deployment and a regular, a actual base station deployment. The right hand side is the actual base station deployment, and you can see it is not like PPP, which is in the left, but it's also not very regular. Those points are not put in a grid, proper grid, but they are perturbed by some random factors. We can basically say that the real system would be in between these two extremes. One extreme is the PPP case, another extreme is the perfect grid. The real system lies somewhere in between. So we also hope the coverage probability should also of a real world system should also be between these two extremes. And this is actually true. This results shows uh, the coverage performance of a 5 cross 5 square grid and the PPP and an actual base station deployment. And you can see that the Poisson deployment has a lower probability of coverage, and that is because some base station can be very close and this can cause a lot of interference, while the square grid actually have a higher coverage, and the real base station location have a coverage in between the two. So we see that both cases, whether we model using the grid model, or we calculate using the PPV model, both are wrong by the same amount, or you can say accurate by the same amount. So there is some gap between these two curves. Now the question is, since simulation and analysis both gives you little bit inaccurate results, but the analysis gives you a capability to understand those insights, derive and design systems better, analysis can very well be treated as a tool and has some bigger advantage here. Simulation can be time consuming, doesn't give you insights, but analysis can very well give them insights. And moreover, we saw both of them are not exactly accurate, but they have the same inaccuracy compared to the real world base stations. Up to now, we are mainly talking about the SINR coverage probability. So basically that characterizes the SINR performance of network. Another important metric is the rate achieved by each user. Okay, and as you know, in modern cellular networks, there are multiple users which are associated with base stations. So base station has to schedule all those users, give them sufficient proportional resources, and based on that the rate is calculated. So if there are more users than the number of base station, each base station will have more than one user. And you know, because of the association, all users which fall in the base station association area has to be served by that base station, right? If we suppose talk about this average receive power based association, then each user will see which base station is the closest one and get associated with that. And it may happen that more than one user will have one particular base station as the closest base station. Now the base station has limited time frequency resource, right? Suppose total bandwidth it has is B. If there are multiple base stations, multiple users associated with this base station has to divide the resources among all users. Okay, so suppose each user get resource is equal to W. Okay, this can be in terms of time or frequency. Both are equivalent resources. So in that case, the data rate achieved by each user would be equal to the resource available, which is W, multiplied by log 2 1 plus a sin r. This is a very simple upper bound from the Shannon theorem, and of course when you implement in practically you will achieve data rate less than this because of various practical constraints. This will denote the number of bits a user can send per second. Okay, this is in BPS. Now we can see if a user get more time resource or frequency resource W, then it will have a higher data rate. SINR, of course, if you increase the SINR, you will get higher data rate. Now, how this W depends on P, right? We can of course understand the number of users plays an important role. If you have more number of users, each user will get less time resource. So how does this total bandwidth B, each user's bandwidth W and total number of users N depend on each other? That depends on the multi-user access. One of this multiple access technique is OFDMA. And most of the modern cellular networks right now use OFDMA, which is orthogonal frequency division multiplex access. So what is done in OFDMA is the total frequency band and the available time slots are divided into small chunks, okay, of some frequency band and some time slot. Now each one resource is known as the resource block. Now each user is assigned a different resource block. So now the interference, because it is only caused among the devices which are using the same frequency band and at the same time, the two user will not see interference from each other because they are assigned a different frequency time block. Now suppose consider a case where base station has total bandwidth of 10 megahertz and the total time of transmission is 1 second. So what base station can do is divide the 10 megahertz band into 100 kilohertz subbands, and the time slot is also divided into small slots of 1 milliseconds. Okay, so now if you give one slot to one user, so that user can transmit up to the available bandwidth, which is 100 kilohertz, into log 1 per second into, that is bits per second, multiplied by the time slot he gets, which is 1 millisecond. So total number of bits he will transmit will be equal to this. Now instead, if you give him the whole slot, you will need to give him 1.1 kilohertz instead to get the same rate. Okay, so instead of dividing the time and frequency both, you could just divide the frequency of 10 megahertz to subbands of 0.1 kilohertz, and you don't keep the time slot intact. And then if you divide this way, theoretically you will also see the same rate in both cases. So in this way, you can assign up to 1 lakh users to each base station. And of course, if your total number of users are less than this, then you can assign single user more slots, and that will just increase the rate for each user. Okay, so because the time and frequency division is kind of equivalent, we can sometimes just say that we are dividing the frequency instead of talking about the time frequency resources. We have multiple resource blocks and multiple users. How do we assign these resource blocks to users? Okay, not all users are same. Some users may require more data, some may require less data. Some users may have very good channel, some may have very bad. So there are multiple ways you can divide these resources to users, and that is where scheduling comes. We take a very simple case, which is round robin scheme, in which you divide the resources equally among users. So if base station has 50 users and total bandwidth is B, then you divide by B by 50, and that will be the bandwidth to each user. And you can understand time, frequency are similar resources, so you can either divide in frequency or either divide in time, or you can also divide in both dimensions. It should theoretically give you similar rates. So now if you talk about the typical user for which we calculate the SINR, okay, it is associated with a base station, which is we call it tag base station, and the cell of that base station is called the tag cell. So now this base station who is associated with this typical user may have more base station. Suppose it has n more base station, the typical user will only get b by n bandwidth, because the rest of the bandwidth will be given to the other users. Now, first thing is we have to characterize this number of base stations, number of users which are connected to this tagged cell. Okay, and one thing to notice is it is also a random variable. Why? Because the base station locations are random. So each cell of the base station will also be random. It will have some distribution, and then in that area the number of users is also random, because number of users are coming from a point process itself. So if you assume a PPP distribution of users also, then given the area, number of users will be a Poisson random variable with parameter user density multiplied by the area of the cell. Now area of the cell itself is a random variable, so we have to characterize these two random variables, and then only we can know what is the distribution of number of users in the tagged cell. Okay, so we will start with the one-dimensional case just for example, and then we will see how we can change this analysis to 2D case. So if we talk about the one-dimensional case, in the one-dimensional, the base station Poisson point process will look like just points on a single line. Okay, so suppose in the positive axis, the points are x1, x2, x3, and x1 is the closest point from the origin in the positive x-axis. Then similarly on the negative axis we have x minus 1, x minus 2, x minus 3, and same way we just say that x minus 1 is the closest point from origin in the negative x-axis. Just for the simplicity case, this x minus 1 and x minus 2, all these are negative values, so we also save its absolute values in variable yi. So yi is nothing but the absolute value of x minus I, which is minus x minus I for negative values. Okay, now the origin is met1. So if the user is there, it will connect to the closest base station. Now the closest base station can be x1 or x minus 1 depending on whoever is closer. So if x1 is closer than x minus 1, which means x1 is less than y1. Okay, remember y1 is the absolute value of x minus 1, which means it is the distance from the origin. So if the distance of x1 from the origin, which is x1, is less than the distance of x minus 1 from the origin, which is y1, then the origin will be in the associated with x1, or it means that origin will be in the Voronoi cell of x1. Okay, suppose this is the case. Now let us create the Voronoi regions. So these are denoted by the red marks on the line. So you can see, take an example of x1 and x2. So the cell will be divided exactly in between of x1 and x2. So all the points which are between x1 and the red point will be in x1, and all the points will be between red point and x2 will be in x2. Okay. Similarly, if x1 is closer to origin, the uh, red line which will denote the cell of x1 will also carry origin. It means red line will be on the left hand side of the origin. Okay. So the cell Voronoi cell of x1 to which origin is connected will be on the right hand side. This will be the midpoint of x1, which is x1 plus x2 by 2, and on the left hand side it is the midpoint of x minus 1 and x1, so it will be equal to x minus 1 plus x1 by 2. Okay, now what we want to do is to calculate the area or length of this Voronoi cell. Remember, in 2 dimension it is the area, in 1 dimension it is the length of the tagged cell. The length of this tagged Voronoi cell is equal to the right hand limit, which is x1 plus x2 by 2, and the left hand limit, which is x minus 1 plus x1 by 2. Okay, now you can see this x1 will cancel, but we are not cancelling it. The reason will appear shortly. So now this can be written as half of x2 minus x1 plus half of x1 minus x minus 1. Okay, now we will just write x minus 1 as minus y1. So the equation will become half of x2 minus x1 plus half of x1 plus half of y1. Okay, now you can see x1 is the distance from origin to the closest point. So from the PPP we know the distribution of the distance of the closest point from the origin is a exponential random variable with parameter lambda. Similarly, y1 is also the distance of the closest point in the negative y-axis. So it will also be an exponential random variable. Now x2 minus x1 is the distance of the closest neighbor from x1. So that is also the exponential random variable. And these are all independent to each other. So x2 minus x1 is an exponential random variable, x1 is an exponential random variable, y1 is an exponential random variable. So sum of these three will also be a gamma random variable with parameter 3. So sum of three exponential random variable is nothing but a gamma random variable with parameter 3 and lambda. So half of this would be the, what will it will be? It will be a gamma random variable with the 3 parameter, only the rate will change. So in this case, the summation of these random variable is gamma random variable parameter 3, and the Voronoi cell length is half of this, so it should be equal to gamma random variable with parameter 3 and rate 2 lambda. So this is the distribution of the Voronoi cell. Now condition on the length of this Voronoi cell, if we assume PPP users, then condition on this length, the number of users which are falling in this cell is a Poisson random variable with parameter lambda u, which is density of users, into length of area, which is length of region, which is A. Okay, so Poisson means it has the following distribution. So now this is condition on A. If we decondition with respect to A, we will actually get the distribution of total number of users in this tagged cell. Okay, and notice one user is already there, which is a typical user, and we are conditioning on that presence of that user, and we calculating the performance condition on that user. So if you remove that user, then the rest of them is a Poisson one process. Okay, so total number of users will be actually 1 plus the number of other users. And number of other user is n dash here, which is a PPP, which is a Poisson random variable. Okay, so when we decondition with the distribution of A, we just integrate with respect to distribution of A. That is simple with some manipulation. Then remember the total number of user is n, which is equal to n dash plus 1. So probability that n is equal to k is same as probability that n dash is equal to k minus 1. From the result in the previous slide, we put the value here and we manipulate, solve it, and finally we get a distribution of the following format. From this distribution, we can also calculate the mean of number of users present in the tag cell, and that is given as 1 plus lambda u into expectation of A. Right? Remember, n dash is lambda u into A. So the mean number of n dash is lambda u into expectation of A, and number of users is just 1 plus that. So EA is the mean you can compute from the gamma distribution. It will be equal to 3 by 2 lambda. So total number of users will be 1 plus 1.5 lambda u by lambda. Okay, so we have both the distribution of the number of users present in the tag cell and also the number on the distribution of it. That is for the 1D case. Now we are in the 2D dimension, and for this the exact characterization is actually difficult. So there are some numerical results which are given by fitting the Voronoi cell, and one of this result which is popularly accepted in the present literature is that the A, which is the area of the tagged Voronoi cell, which follows a gamma distribution with parameter 4.5 and 3.5 lambda. So 4.5 is the shape parameter and 3.5 lambda is the rate parameter. And similarly, you can calculate the mean from this, and you will get that mean number of users in the tag cell will be 1 plus 1.28 into lambda u by lambda. Okay, so this 1.28 is coming as a factor of 4.5 divided by 3.5, and 1 is coming because of one additional typical user. So with the distribution of n and the mean number of n, we can now compute the rate coverage. Okay, so remember the data rate for each user would be equal to total bandwidth divided by total number of user in the tag cell. This B by N is the amount of bandwidth available to that typical user multiplied by log 1 plus SNR. So rate coverage is nothing but the probability that the rate you are getting is above some threshold rho. Okay, now put the definition RU here. So you will say this is equal to probability that B by N log 1 plus SNR is more than rho. Okay, now this n itself is a random variable, so you have to also compute your expectation with respect to n. Okay, inner term, if you look at, you can do just some manipulation. B by n would go into the division into the other side of the equality, and then log will become exponential and 1 plus become minus 1. So this is same as probability SNR is more than 2 to power rho n by b minus 1. And probability that SNR is above something is nothing but the probability coverage. So this will be equal to probability coverage at threshold 2 rho n by b minus 1. And this is a function of n. So you have to compute your expectation with respect to n. Some people also approximate the result by putting the mean number of n in place of n.